Welcome to the deep dive. Get ready, because today we're diving into something seriously cool.
Yep.
AI that's not just running your code, but actually improving it automatically. We've got some really fascinating research here and a brand new open source project that's taken this on.
That's right. You know, the idea of self-evolving code, it's been around for a bit, genetic programming and all that.
Right.
But it's always been, well, kind of limited. What's really different now, the big shift, is using these powerful large language models, LLMs.
Okay.
And we're going to dig into how these AI brains are being used in a, well, frankly, revolutionary way to evolve and optimize entire code bases. We're talking way beyond just tweaking little snippets.
Exactly. And the project we're focusing on is OpenEvolve. It's an open source implementation of Google DeepMind's really impressive AlphaEvolve research. I mean, think about that. Cutting-edge AI research from a top lab now out there for anyone to grab and use. That feels like a pretty big deal, right?
Yeah.
Putting serious power into the community's hands.
It really is. AlphaEvolve showed some incredible potential, and OpenEvolve is all about bringing that capability to more people, more developers, more researchers.
So what are we covering today?
So in this deep dive, we'll break down the core ideas behind these evolutionary coding agents. We'll look at how OpenEvolve works under the hood, its architecture, basically.
Okay.
And then we'll get into some really compelling examples from the real world, showing what it can actually do, some complex problems it tackled.
Right. So the goal today is pretty straightforward. Give you, our listeners, a clear picture of this major step forward in AI and, what it might mean for different fields down the line.
Let's do it.
Okay, so let's start with the background. This whole idea of code improving itself, as you said, not entirely new. We've had genetic programming concepts.
Yeah, for decades, really.
But the combination, this mix of modern LLMs with those evolutionary ideas, that's where the novelty and, frankly, the power comes in. AlphaEvolve and now OpenEvolve seems like a genuine step change. So what were the key advancements that AlphaEvolve brought to the table, the things OpenEvolve now implements?
Okay, several crucial things. First, using LLMs lets you make really sophisticated changes to the code. These aren't just random mutations. The LLMs can actually sort of understand the code's intent.
Understand it, wow.
Yeah, and make intelligent, context-aware modifications. Second, the whole process has automated evaluation built in, so the LLM suggests a change.
And the system automatically tests it.
Exactly. It tests and scores the new code against whatever goals you've set. Instantly knows if it's better or worse.
Okay, so it's not just guessing. Constant feedback.
Precisely. Third, it's all wrapped in a proper evolutionary framework. So the system keeps iterating, keeps improving, building on the successful changes, discarding the bad ones. Survival of the fittest code, you could say.
Yeah, right.
And maybe the biggest thing, AlphaEvolve and OpenEvolve, too, they're designed to evolve entire code bases, not just isolated functions or little blocks. That whole program approach unlocks a different level of optimization.
Okay, that makes sense. A much bigger scope. So we have this powerful idea. How does OpenEvolve actually do it? What are the bits and pieces inside?
Right, so OpenEvolve runs this smart evolutionary cycle. It's got four main components working together. First up is the prompt sampler.
Prompt sampler?
Yeah, its job is basically to create really rich, detailed prompts for the LLMs. These aren't simple instructions. They include the current code, sure, but also stuff about previous versions, how well they scored, the original problem description, all the context.
So you're giving the LLM the full history, like, here's what we tried, here's what worked, here's what didn't, now give us something better.
Exactly that. It gives the LLM the background needed to make genuinely informed suggestions. The second part is the LLM Ensemble.
Ensemble, meaning more than one.
Yep. Instead of relying on just one language model, OpenEvolve uses a whole group of them to generate code modifications.
Why do that?
Well, different models have different strengths, right? One might be better at logical leaps, another at refining syntax, another might just have been trained on different data. Using an ensemble gets you more diverse ideas, potentially more creative and effective solutions.
Interesting, like having a committee of AI programmers brainstorming.
Sort of, yeah. Then third, you've got the evaluator pool. Once the LLMs generate these modified programs, this pool takes over.
The testing part again.
Right. It automatically runs tests, checks against the requirements, and assigns scores. That immediate feedback loop is absolutely critical for guiding the evolution. Tells the system what's working.
Makes total sense. You need that objective measure. And the last piece.
The fourth component is the program database. This is basically the system's memory. It stores all the programs that have been generated and evaluated, along with their scores and other metrics.
So it learns over time.
Exactly. It uses this history to guide future evolution, steering it towards more promising areas it's discovered. And coordinating all this is a controller. It manages these four parts in an asynchronous pipeline.
Asynchronous, meaning they work in parallel.
Yeah, think of it like an assembly line. While one potential solution is being evaluated, the LLMs can be working on generating the next one, and the prompter can be preparing the context for the one after that. It makes the whole process much faster and more efficient. You can explore way more possibilities.
That sounds like a really slick setup.
Mm.
Very efficient.
Mm.
Okay, so beyond those core parts, what are some of the other, key features that make OpenEvolve stand out, make it flexible or powerful?
Yeah, there are several important ones. We mentioned evolving entire code files, which is huge. It also supports multiple programming languages, so it's not just stuck on, say, Python.
Versatile.
Very. Then there's multi-objective optimization. This is really powerful. It means you can tell OpenEvolve to optimize for more than one thing at the same time. Like, make the code faster and use less memory. Or maybe optimize for speed and code readability. Or even energy efficiency, depending on your goals.
Oh, okay. So you could say, make it fast, lean, and easy for humans to understand. That's quite something.
Exactly. You define the objectives. Other key things. Flexible prompt engineering, so users can really tweak how the LLMs are guided. Distributed evaluation, which lets you spread the testing workload across multiple machines, essential for big problems.
Speeds things up.
Massively. Then the LLM Ensemble approach we already talked about, and also a checkpoint system.
Ah, so you can pause and restart it.
Crucial for long evolutionary runs. You don't want to lose days of computation if something glitches.
No kidding. Okay, this all sounds incredibly promising, powerful stuff in theory. But how does it hold up in practice? The source material digs into two really cool examples. Let's start with the circle packing challenge. What's that about?
Right, circle packing. It's a classic optimization puzzle. The basic idea is you have a set of circles, maybe different sizes, and you need to fit them into a container, in this case, a unit square, like a 1-by-1 box.
Okay.
The goal is to arrange them so you maximize something. Here, it was maximizing the sum of the radii of all the circles you can fit in. Google's original AlphaEvolve paper reported packing 26 circles and getting a total radius sum of about 2.635.
So OpenEvolve tried to replicate that. How did it start out? What was its first attempt like?
Yeah, they set it the same task. Its very first solution was, well, pretty intuitive. It placed a big circle right in the middle of the square
Makes sense.
and then arranged rings of smaller circles around it. The initial code basically calculated center points based on angles and distances from the center. This first try got a sum of around 1.87.
Okay, a decent starting point. A logical first guess, I suppose. But I'm guessing it didn't stop there. What happened by, say, generation 10?
Right, evolution kicked in. By the 10th generation, OpenEvolve had already found a significantly better arrangement. It discovered a hexagonal packing pattern, which is known to be more efficient for circles.
Ah, like a honeycomb.
Exactly. The code changed, too. It started using named parameters like Serraner for the middle circle's radius and earring 1 for the first ring's radius. And the positioning logic reflected that hexagonal structure. This bumped the score up to about 2.18.
Nice improvement. A definite step towards better packing. What about later on? Generation 100, did it change strategy again?
It did, quite dramatically. Around generation 100, it shifted away from the central cluster idea towards a grid-based approach.
A grid, like rows and columns.
Yeah. The code started defining rows of circles with specific XY coordinates. It seemed like a more systematic way to fill the space. This grid strategy got the sum up to about 2.32.
So it explored different fundamental layouts, central, than grid-like. But the really big leap came later, didn't it? The final solution.
Absolutely. This was the most impressive part. OpenEvolve eventually discovered the power of using external mathematical optimization libraries. Specifically, Python's scipy.optimize.
It figured out how to use a library.
Yeah. The evolved code defined an objective function, basically, the thing to minimize, which here was the negative sum of the radii, since scipy.optimize minimizes, and it defined constraints. Circles can't overlap, and they all have to stay inside the unit square.
Yeah.
Then it just called the minimize function from scipy using a specific algorithm called SLSQP to find the optimal positions and radii, and the result? A sum of 2.634.
Wow, 2.634. That's incredibly close to the original AlphaEvolve result of 2.635.
It's basically identical within the margin of error, and the amazing thing isn't just the score, it's how it got there. The system wasn't told to use SciPy, it discovered that leveraging this powerful mathematical tool was the best way to solve the problem. That's a huge leap from just rearranging circles.
That's mind-blowing. It didn't just optimize the parameters of one strategy, it found a completely new, more powerful strategy. Now, the source also mentioned they used a two-phase approach for this evolution. Why split it up?
Good question. That seemed key to getting this result. They realized the search space was really complex. So phase one was all about initial exploration.
Okay.
The focus was on trying out fundamentally different approaches, like the central cluster versus maybe other constructor-based ideas. They used a population size of 60 programs split into 4 islands. Think of these as separate little evolutionary pools that occasionally share good ideas.
Islands. Interesting.
Yeah, it helps maintain diversity. And they used a high exploitation ratio of 0.7. High exploitation means the system focuses more on refining the best ideas it already has rather than trying wild new things. So phase one was about exploring broad strategies and improving the promising ones.
Got it. Cast a wide net, see what looks good, then polish it. What about phase two?
Phase two was called breaking through the plateau. They noticed progress slowing down, so they shifted gears. The goal now was more radical innovation. They increased the population size to 70, used more islands 5, and crucially reduced the exploitation ratio to 0.6.
Lower exploitation means more exploration, more weird ideas.
Exactly, more encouragement to try novel things. And here's a key bit. They also updated the prompt they gave the LLMs. They specifically added hints suggesting it explore optimization techniques, like using libraries.
So they gave it a nudge in the right direction.
They did. And that targeted guidance, combined with the shift towards exploration, seems to be what unlocked that final SciPy breakthrough. It shows a really smart way to manage complex searches, broad exploration first, then maybe some hints, and more focus on radical changes to break through limits.
That makes a ton of sense. Explore, then exploit, then maybe explore again with some guidance.
Okay, let's move to the second example. Minimizing a complex function. What was the challenge there? Right, this was a different kind of problem. They gave OpenEvolve a mathematical function, fxy equals sin x plus sin plus by 2 plus y2 20. It's what's called a non-convex function, meaning it has lots of bumps and dips, multiple local minima. Think of a hilly landscape. There are lots of valleys, but only one is the absolute lowest point globally. Finding that global minimum is tricky because algorithms can easily get stuck in a nearby but not the lowest valley.
Okay, like getting stuck in a small ditch instead of finding the Grand Canyon.
Hey, exactly. The true global minimum for this function is around x 1.704, y equals 0.678, with a value of about negative 1.519.
And what algorithm did they start OpenEvolve with, the basic one?
They started it with a very simple random search. The initial Python code basically just loops many times, picks random x and y values within a certain range, like -5 to 5, calculates the function's value at that random point, and keeps track of the lowest value it's seen so far.
Super simple. Just guess a bunch of times and hope you hit the lowest spot. Probably not very efficient for tricky functions, right?
Generally, no. It can work for simple things, but for a non-convex function like this, it's likely to miss the true global minimum. It's a baseline.
So what did OpenEvolve evolve it into? What was the improved algorithm?
Through evolution, OpenEvolve arrived at a much more sophisticated algorithm, simulated annealing.
Simulated annealing. I've heard of that. How does it work?
It's inspired by the process of annealing metals, actually. The evolved code introduced several key concepts. It maintains a current best solution. Then it makes small random changes or perturbations to that solution to explore nearby points in the landscape.
Okay, like taking a small step from where you are.
Right. But here's the clever part. It doesn't always move to a better spot. It uses a temperature parameter. If the new spot is better, it always moves there. If the new spot is worse, it might still move there sometimes.
Move to a worse spot. Why would it do that? That sounds wrong.
It sounds counterintuitive, but that's the key to escaping those local minima. By occasionally accepting a worse move, especially when the temperature is high, the algorithm can climb out of a shallow valley to potentially find a much deeper one elsewhere.
So it can go uphill temporarily to get over a ridge and find a better valley on the other side.
Precisely. The probability of accepting a worse move depends on how much worse it is and the current temperature. The temperature starts high, allowing lots of exploration, lots of climbing out of valleys, and gradually cools down over iterations.
And as it cools down?
As it cools, the algorithm becomes less likely to accept worse moves, eventually settling down into the best minimum it's found. The evolved code included this temperature concept and a cooling rate to manage how quickly it cools.
So it's like shaking a ball in that bumpy bowl again.
Yeah.
Shake hard at first to explore, then shake gently to settle in the deepest part.
That's a perfect analogy. What's remarkable is that OpenEvolve essentially rediscovered the core principles of simulated annealing: local search with perturbations, the temperature-based acceptance to escape local minima, the cooling schedule to control the search, and even tuning the parameters for better performance. All evolve from simple random search.
That is genuinely impressive. Going from random guessing to a well-established, complex optimization algorithm like simulated annealing, it really drives home the potential here.
Okay, now a critical piece of this puzzle seems to be the LLM ensemble. The source had some interesting points on how different models performed. What did they find?
Yeah, the choice of LLMs definitely matters. One big takeaway was that latency, how fast the LLM responds, is super important.
Why is that?
Because evolution takes many, many generations. You're calling the LLM thousands, maybe tens of thousands of times. If each call takes a long time, the whole process grinds to a halt. So faster models are generally better, even if they're slightly less smart.
Speed matters. What else? They also found that model diversity is a good thing. Using different LLMs in the ensemble seemed beneficial. Different models have different strengths, different ways of thinking, maybe different training data.
So mixing them up gives you a better shot at finding good, creative solutions, like getting opinions from different experts.
Exactly that idea. The best general combo they found in their tests was using Gemini Flash 2.0 Lite together with the slightly more powerful Gemini Flash 2.0.
Okay. Any standouts for speed?
Interestingly, they noted that Cerebra's AI's API gave them the fastest inference times, which could be a big advantage for rapid evolution.
Good to know. And did the best combo change depending on the task?
It did. For that specific circle packing problem we discussed, they actually found that a combination of Gemini Flash 2.0 and Claude Sonnet 3.7 worked best.
Huh. So the best LLM setup might depend on the specific problem you're trying to solve. That's fascinating. What's the main lesson here about the LLMs?
I think the key insight is that it's a balancing act. You need to balance the speed of the LLM with its quality or sophistication. The findings sort of suggest a potentially smart strategy. Maybe use faster, cheaper models for the bulk of the evolutionary steps for rapid iteration.
Get lots of generations done quickly.
Right. And then maybe strategically bring in the more powerful, maybe slower or more expensive models at certain points, perhaps when progress stalls, or to explore really complex, nuanced changes. It's about optimizing the whole evolutionary process.
Optimizing the optimizer. Makes sense. Okay, so for people listening, maybe programmers or researchers who are thinking, wow, I could use this. How easy is it to actually get started with OpenEvolve? Can they just download it and run it?
It actually looks pretty accessible. The source mentions the standard GitHub way. You use git clone to copy the repository to your machine and then pip install AT to install OpenEvolve and its dependencies. Seems fairly standard for Python projects.
Okay, installation sounds straightforward. What about actually using it? Do you need to be a super expert?
They provide a Python API, which looks quite user-friendly. The example snippet shows you basically initialize an evolve object. You tell it where your starting code file is, where your evaluation script is, the thing that scores the code, and where your configuration file is.
Configuration file.
Yeah, we'll touch on that. But once it's initialized, you just call a method like evolve.run and tell it how many iterations, how many evolutionary steps you want it to run for.
And it just goes.
Pretty much. It runs the whole evolutionary loop we talked about, prompting, generating, evaluating, updating the database for the number of iterations you set. Then it returns the best program it found and its performance scores.
That does sound quite manageable. Is there a command line option too for people who prefer that?
Yep, absolutely. There's a command line interface as well. The example shows a simple command, .python, openevolve-run.py. Then you pass the paths to your initial code, your evaluator script, your config file, and maybe some settings like the number of iterations directly on the command line.
Okay, so flexible options there. You mentioned the configuration file. What kinds of things can users control there? How do you tune OpenEvolve for different problems?
That config file seems pretty important for customization. It's typically a YAML file, which is easy to read and edit. The source gives an example showing key parameters.
That's just
Things like max iterations, how long you want the evolution to run. The Elms section is crucial. You specify your primary model and maybe a secondary model for the ensemble, and you can set the temperature for the LLMs.
temperature affects creativity, right?
Exactly. Higher temperature means more random, potentially more creative outputs, while lower means more focused and predictable. Then there's the database section where you control the evolutionary dynamics, things like the population size, how many programs in each generation, the numislands, and that exploitation ratio we discussed earlier, balancing refinement versus exploration.
That sounds like a good amount of control to tailor it to your specific problem and maybe your compute budget.
Yeah.
Okay, last practical question. How do you prepare your own code, your own problem, for OpenEvolve? What are the steps?
Seems like a few key steps. First, you need to go into your existing code file and mark the specific block or blocks of code that you want OpenEvolve to actually change. You do this with special comments, #evolve block start and #evolve block end.
Ah, so you tell it exactly which parts are fair game for evolution.
Precisely. It won't touch anything outside those blocks. Second, you need to write that evaluation function or script we mentioned. This is custom code you write that takes a candidate program, generated by OpenEvolve, as input and outputs some scores or metrics telling OpenEvolve how good that program is.
So you define what better means for your specific problem.
Exactly. Speed, accuracy, memory usage, whatever matters to you. Third, you create that YAML configuration file, pointing OpenEvolve to your starting code, your evaluator, and setting those parameters like LLMs, population size, etc. And fourth, you just run it, using either the Python API or the command line.
Okay, that sounds like a clear, structured process. Mark the code, write the judge, configure the run, and let it go. Makes sense. Looking forward now, what's next for OpenEvolve? What are the developers planning?
They have some exciting future directions planned. One big one is supporting more LLM providers, probably through standard APIs like OpenAI's or maybe interfaces like LeadLM. That gives users way more choice in the models they use.
More options are always good. What else?
They're looking at improving the prompt engineering side, maybe making the prompts adapt automatically based on how the evolution is going instead of just being static.
Smarter prompting.
Yeah. Also, thinking about more sophisticated evaluation cascades. Maybe quick, cheap tests first, and only run expensive, thorough tests on the most promising candidates. Make evaluation more efficient.
That sounds smart. Anything else on the horizon?
Two more things mentioned. Possibly developing a graphical user interface, GUI, for monitoring and maybe controlling the runs, which could make it more accessible for some users.
A dashboard, maybe?
Could be. And finally, they plan to expand the library of examples, showing how to apply OpenEvolve to a wider variety of problems. That would really help new users get started and see the possibilities.
It definitely sounds like an active project with a clear roadmap. Lots of potential still to unlock.
Yeah.
Okay, let's try to wrap this up. To summarize, what's the big picture here? Why is OpenEvolve significant?
I think the real significance is that it's democratizing this really advanced AI capability, AI-driven algorithm discovery. It's taking the groundbreaking ideas from a top research lab like Google DeepMind's AlphaEvolve and making them available as an open source tool that anyone can use, experiment with, and build upon.
Yeah, moving it from the lab into the hands of the broader community.
Yeah.
And the examples we talked through, like the circle packing getting so close to the original result and evolving random search into simulated annealing,
Yeah.
they really showcase what's possible, don't they?
They absolutely do. I mean, the fact that a system can autonomously discover and implement fundamentally different and more powerful strategies like switching from geometric patterns to using a mathematical optimization library or evolving a sophisticated algorithm from scratch that's not just incremental improvement, that shows the potential for genuine automated discovery using these guided evolutionary methods with LLMs.
So, for our listeners out there working on tough algorithmic challenges in science, engineering, finance, whatever, this could genuinely be a new tool in their toolkit.
It absolutely could. We definitely encourage you, if this sounds interesting, to check out OpenEvolve. Explore the code, read the documentation. You can find it all on GitHub. The main repo is at github.com/code-lean-OpenEvolve.
And the specific examples.
Yeah, they have dedicated folders for the circle packing and function minimization examples right there in the repository, so you can see the actual code that evolved. And reading the original AlphaEvolve paper from DeepMind is also highly recommended for more background.
Excellent. We'll make sure those links are available.
Okay.
Okay, so to leave our listeners with something to think about, here's a final thought. We've just discussed AI that doesn't just run code, but can fundamentally improve it, optimize it, even discover entirely new algorithms for solving problems.
What are the broader implications of that? If AI can start doing the invention part of problem solving, what kind of future innovations might that unlock? And how could it change the very nature of software development, scientific research, and discovery itself? It's a huge question, definitely something worth pondering. Thanks for joining us for this deep dive.